I'm Gary Greider. I'm the High Performance Computing Division Leader at Los Alamos. Dominic Manna was supposed to give this talk, but he couldn't. And so he works for somebody who works for somebody who works for me. So that's an indication of how high of a level I'm going to be giving this at compared to what Dominic was probably going to do. So sorry for that. So this is really, I put that second title in there, making computational storage consumable for HPC. I think consumability is really important, and we've learned that over the many years we've been working in this space. And it's also really nice not to have to say what Los Alamos does after the big grand movie that came out. We don't have to explain what we do anymore. Everybody just knows, so that's kind of nice. So computational storage, why? So I always start this slide by talking about we're the poster child for computational storage, especially reductions. And why do I say that? Well, we have these big supercomputers. You know, the current one has 4 petabytes of DRAM and some ungodly amount of, 100 petabytes of storage, very, very parallel. An application will run on the thing for 6 months on the whole thing and write out a petabyte every hour or something. And so, it's really big, it's really wide, it's really parallel. We produce a lot of data, but we very seldom read very much of it. Why? Because we're not interested in all of it, but we don't know that when you're simulating it. Think about a shock wave going through a material, and you really only care about where the shock wave is. Of course, the shock wave is going to move some femtosecond later, which is another time step for us, but anyway, you can throw away a lot of the edge data, and you just really worry about the pieces that you care about, which turns out to be many times orders of magnitude less data read than written. It's just hard to figure out where that is and what to pull out without pulling all of it back and looking through it in memory. And so I think we're one of the poster children for this, and this is one of the reasons why we've been engaged as a user of the technology probably longer than maybe just about anybody. So what do we need? We need flexibility for where the computation is done, and we need it to be flexible over time because economics will change. Sometimes there's not enough memory bandwidth in CPUs, and you got to move the process somewhere else, like you're copying, right? And sometimes the processors have lots of memory bandwidth, and you do it anymore. And so economics will change, especially if you're as old as I am, they'll change a lot. And so you need to be able to move it around a lot. It's not just energy and time to insight. It's also the size of the analytics machine that you have to build to analyze all that data. Let's say you get 100 petabytes of data. How do you look at that? Well, you probably pull it into a memory that has a petabyte of DRAM, time step by time step, and analyze it. That's an awfully big machine to do data analysis. And so it's as big as the machine that was, that created the data, and that's unfortunate. So we'd like to make those analytics machines smaller. We think we can do that with offloads. There's a couple of ways that we've looked at offloads over the years. One is what we call data agnostic offloads, which is things where the computational storage device doesn't have to understand the format of the data. It's just blocks and bits and bytes. And then there's data aware offloads, and that's where the storage device actually has to understand the format of the data. Sometimes, again, you can get multiple orders of magnitude reductions, and you have a hard time finding what you're looking for. So you've got to filter it and index it and do anything you can to try to figure out how to cut the amount of data you read. And you need to write the data out, perhaps pre-indexed, and not affect the write speed, because the write speed is all important because that's how fast the simulation runs. So you're tying up a $250 million supercomputer writing out data, you don't want to do that. And for science, these data-aware offloads sort of fall into what I would call 3 categories. One is particle methods or point methods in simulation land. And those align really well to row-oriented solutions. So think KV stores. And in fact, there was a talk just given 2 or 3 hours ago by Ching from LANL, and it was talking about the application that this represents. And then there's the grid methods, which are not point methods. And those are very columnar based. In fact, all of those codes think of themselves as just distributed columns of data, distributed arrays, right? Across a million memories maybe, and maybe it's really large, but it's just a distributed array, a set of those. And then there's combinations, right? Large, complex grid methods that are really ugly, and we're just gonna have to throw everything we have at it to try to figure out how to get on top of being able to do analytics with that kind of data. So that's basically our motivation. The first project that we worked on actually was Stephen down here and SK Hynix. Jen is in the room somewhere, was ABOF. And ABOF was essentially a data agnostic offload, and it looks an awful lot like what Kim Malone and Bill Martin talked about yesterday, with our TP4091 work. Is basically we took ZFS. ZFS is a popular file system. We like it. It's a kernel-based file system. It's very, very resilient, has a lot of resilient features. And we basically said, well, when we run this on a server over here to the right on the graph, and you have, say, 20,000 megabytes per second, 20 gigabytes per second of flash hooked up to the server. If you turn on, checksum, you don't get anywhere near 20,000. If you turn on, heavy duty compression, you get nowhere near. And if you turn on really super heavy duty compression, you're down in the single digit gigabytes per second. And so we love ZFS, but it's pretty intensive, especially if you're doing heavy compression. And by heavy compression, like gzip, where you have a Huffman table and you've got to go over and over the Huffman table a bunch of times. So you're using an awful lot of memory bandwidth, and servers typically don't have enough memory bandwidth to do this well. And so offloading it makes a lot of sense, and pipelining it makes a ton of sense. And so this was an effort to try to, fix that and make ZFS be as fast as XFS, which everybody would love, right? And there's two pieces of that. One is we needed direct I/O in ZFS, and the developer for that is sitting in the room somewhere over there. And the other was this offload work. And the offload work is sort of predates, I think, a lot of it's a very, very early example of how to do, offloads. And if you'll notice that in that bottom left corner there, we copy the data from the host down to the device. So essentially we sort of do a remote malloc, if you will, copy the data down to the host, and then tell the device, hey, now do erasure, hey, now do compression, hey, now, and then eventually we say, hey, you're a peer to the device, here's where you put it, just go put it out there on the device for me. And the offload was great. We got a lot of performance out of it. But what I think was really cool was we wanted a solution that you could run anywhere. And so the cool thing about this is the bits that are written out to those NVMe devices are the same bits that if the software had written it. And so if you turn that accelerator off, you can still go read that file with ZFS. If it's compressed, if it's erasured, whatever it is, it will work because it's identical. The bits you wrote were identical. And which means that you can kind of run these things anywhere you want to run them. And in fact, take accelerators away. And if you add accelerators, it just goes faster. But you can live without them. So anyway, you can see we had a great partnership with a bunch of really good people to work with. And this was pretty nice work. And it's all being upstreamed. ZFS will get the bits at some point. And there's even a kernel module that you register, hey, I do compression really, really well, or hey, I do erasure really, really well. And any storage system in the kernel that wants to use those services can just use that plugin to access those services. So anyway, all that stuff is open, being upstreamed, and between that and the direct I/O, maybe we'll get ZFS to be XFS for performance, but ZFS for reliability, or close. Moving on, so data aware. That was data agnostic. This is data aware. We've done a couple of projects in this space, and we learned a lot from that. The first one was a row-based. So this was a point method. So it was a particle and cell code, a point method. And we did some early work at CMU on this. Ching, the student that gave the talk, he's from CMU. Garth Gibson's last student before he left, if you remember Garth. And He actually wrote this Delta FS paper, which was the best student paper at SC19, and it was really pretty cool. So we have this simulation called a particle and cell simulation, and the particle and cell simulation works like this. There's 1 million cells, and there's 1 trillion particles, and the particles are moving around in the cells because they're being pushed around by momentum and things, right? And so these particles move around, and every time step, it stops, and we write out a petabyte of particles. And the particles are tiny little records, particle ID, which is like 2 bytes or something, enough to keep 1 trillion, and energy and location. And by location, you sort of mean where it's at, or the cell, essentially, that it's in. And the way the application was writing the data out was in flat files. Big old flat file, petabyte, write it all out there. It's great. How do you at the end of this simulation, what they want to do is they want to take the 1,000-ish most energetic cells or particles, and they want to ask the question, hey, where have those particles been? Where did they go in that cell structure? Where have they been? And so originally the way the application wanted to do this was it wanted to read all petabyte in and just go find this stuff and make a log of where they've been, which meant reading 100 petabytes, which we do, but we don't like doing it. And so we said, hey, let's, and the application programmer said, well, is there a better way to do this? And he came to us and he said, I want to write a file per particle per time step. And we said, that'll work, 1 trillion files per time step. Let's do that to our file systems. Talk about denial of service, right? And so we said, no, that probably won't work, but we can make it so that you think you're writing little files, but really you're writing records. And we had a perfect way to shard those records, and that they were sharded on particle ID, which is a perfect shardable thing. And so we fired up 1,000 level DBs, and we assigned the first set of particles to one and the next set of particles to the other, so that when everybody wrote their data out, they wrote it out essentially through KV. And we had to use bulk puts because we didn't want to do 1 trillion RPCs and all that kind of stuff. Anyway, we wrote it all out there, and then when they retrieve it, they just tell us the 1,000 particle IDs, and we go get this stuff just like that. So instead of moving up 100 petabytes, they had their answer in 4 seconds or something, and which is amazing, or it was amazing to them. Subsequently, we put this stuff basically almost all in hardware, thanks to SK Hynix, the people there are just totally crazy good with this stuff. And we just recently won an R&D 100 award for this. And this was really cool work. And I think it's technology that maybe is even a little bit before its time. But it's important because it's different than a simple hash key value store. It's an ordered key value store. You can poke into the index and iterate forward in the index or iterate backwards in the index. You don't have to know the key. It's not just a hash. It's really work. It's really hard work that was done here to make this work. And what would we use it for? We use it for making order out of orderlessness. Columnar methods, those are for our grid methods. We're working on those now. We did a quick demo with Seagate, really good set of people at Seagate. And this was with their KV HDD, aka kinetic. And essentially we asked that, we basically wrote Parquet records out, this columnar data. We wrote Parquet chunks out to this through the KV interface that the kinetic has, and basically wrote objects out there, and then had the device, look stuff up using the indexes in Parquet. And this wasn't incredibly useful long-term research, but it helped us understand a little bit about, can a little bitty ARM processor do Parquet fast enough, as fast as the host would by sending all the data to the host? And we got the answer pretty positively, yes. This seems very, very possible, even at single flash device rates. And so we learned that it isn't terribly consumable because we hit it all under ZFS. But the top one, I think, is pretty consumable. You could actually run this as an accelerator underneath rocks pretty simply, I think. Or you could not you have to have rocks at all and still get use out of it. So pretty cool stuff. So what have we learned? Well, we've learned that, if you want to do data agnostic offloads, there things like erasure and compression and pipeline functions are pretty good candidates, and you win pretty big in that space if you have a bandwidth problem. We've learned that we're the poster child for wins on reductions. Reducing the amount of data we move is important when you deal in petabytes on an hourly basis. And we also learned that consumption models are super important. You've got to make these things where they're consumable or they'll have no legs. And so you need to think about things. And I think the ZFS work is a good example of this, right? It depends on ZFS being there. You're not putting the host out of business. You still have a host there. And you can plug the accelerator in or you can unplug it and it will still work. And so it's very friendly to consumability. And we want to do the same thing in columnar. And the leverage that we want to leverage there is the Apache ecosystem for doing analytics. And there's a bunch of things: Parquet formats, Arrow, Substrate, Iceberg. You may or may not know what all those things are, but they're pieces of software from the Apache, analytics community that are for doing data analytics. There's hundreds of analytics packages being used, that are part of that ecosystem. And we want to recognize what we're doing and what we're not doing. And we think that consumers of large-scale data analytics sort of live in two camps. One is you have no idea what you're looking for. You just want a compact representation of it. That's what AI is. That's what you're doing when you train a model, is you're making a compact representation of the data, but you don't know what you're looking for. And then there's you know what you're looking for, you just don't know where the hell it is. That's us. We live in that camp. And we think that is a really good use case for data-aware computational storage because of the reduction. You want to reduce the north-south bandwidth, and you never want to send data east-west. We learned that file systems can be pretty heavy for putting onto devices. Maybe not too heavy. In fact, there's a talk tomorrow from David Flynn about that. But maybe they're too heavy, and blocks don't work at all because you can't do analytics on a block. So maybe object is about the right level of the way to think about this. Anyway, compression, erasure. The Seagate demo actually erasured across objects, so erasure was applied. So it is possible to do this under erasure. But encryption may be one of the hard pieces, right? Because you've got to do key management to devices, which I don't think is really, that's not a thing yet. There's probably ways of doing it though. So let me take you through why we care about columnar so much. So here's an example of a simulation of an eddy, a couple of eddies that are moving through time, and the time steps are located down there at the bottom, 1, 2, 3, 4. So each one of those is a time step in the calculation, and the eddies are forming and moving and swirling. And each one of and if you notice in the green there, all those boxes aren't the same size. Some of them are really big and some of them are really little, and they're really little boxes where you want to resolve the calculation really, really well to understand the phenomenon going on there. And around the edges, you don't care what the phenomenon is, so you unresolve that. Why do we do that? We do that because we're trying to, I have a big machine, 4 petabytes of DRAM. It's about 3 orders of magnitude too small to run the real problem on at full resolution. So I have to do this or I can't run the problem. And so I'm forced into these irregular, ugly data structures, and that's a whole nother lecture on memory bandwidth and why it matters. But this is how simulations work oftentimes. It's called adaptive mesh refinement. And this is a really simple 2D example. The real example is 3D. The real example doesn't use cubes, it uses polyhedrals. It's ugly, it's really ugly. The geometry of how these things work is really ugly. But what you want to do over here in the blue boxes represent you want to make sure that every processor has about the same amount of memory, about the same number of cells, because the amount of work it has to do is roughly equal to the amount of cells it has, because it's updating those cells with the physics. And so basically what happens is you take, you double or quadruple the cells in one place, and you unresolve the other places, and you're pushing the data out to the edges to make sure that the simulation runs fairly balanced. And so that's anyway, that's how simulations work. So each one of those things is a petabyte spread across 1 million memories, and it's arranged in that way. And it's actually serialized. It's serialized because we write it out into files, and it's serialized on this thing called Hilbert order, which is a Hilbert space-filling curve concept for math, where you essentially can draw a line and touch every one of those cells in a memory space. And so it's serialized, so we can serialize it and deserialize it. And each one of those cells has about 100 floating point values in it. Pressure and temperature and materials properties and pressure gradients and all that kind of stuff, right? So there's a bunch of floating point values in each one of those cells, about 100, although we really don't care about all those when we're trying to figure out where the edge of the eddy is. We just care about a small subset. That's important because each one of those things is a column, and when we're going to do a query, we're not going to query over all 100 variables. We're going to query over 3 or 4, which means we're going to get a huge reduction just by using columnar to start with. So anyway, the first question you've got to ask yourself is, okay, you go do this weird stuff, you create all this data. If you wrote it out all in Parquet files as columnar with chunks, why do you need computational storage? What's a point? What's a value? And I said, well, we're not going to query all the columns. We get that win, but we get that win whether we use computational storage or not, right? If you're going to skip over whole sets of data, you're going to skip over whole sets of data whether you're using computational storage or whether the host's doing it. That's not where the win is. The win is because I told you a lie. This is really hard. It really isn't that simple. This is more like what it is, and you're trying to figure out where that little yellow squiggly thing is. And if you knew how much resolved each one of those things is, almost all of the data is in that little green yellow place. Almost the whole data, like 75% of the petabyte is there. And the rest of it is not, we don't care about. And so so the selectivity, we're going to win from columns, absolutely, but we're not going to win very big from eliminating whole row groups. And the reason I know that is because adaptive mesh refinement would have found that and gotten rid of it, and we wouldn't have had that in memory to start with. And if it didn't, we need to go fix it. And so essentially, we're going to have to pry open and look an awful lot of those row groups to find what we're looking for. And we hope we can get an order of magnitude or 2 orders of magnitude of reduction over the whole thing. But it's not going to be done simply by looking at indexes over row groups. That'll help, but not that much. And so we think this is a poster child for computational storage. And we really think that there's this huge community of Apache analytics users that have really hard problems, maybe not quite this hard, but definitely hard problems. And accelerating that all the way down to near storage seems like a reasonable thing to do. So this is our real motivation for where we're going next with all this. So what would it kind of look like? Well, this is sort of a pictorial. The diagram on the left, courtesy of Voltron Data, who's one of our partners, they produce a lot of this software that in the Apache ecosystem. There's dozens of query engines and dozens of different kinds of storage systems you can store these Parquet objects or whatever kinds of objects you're writing out are. And there's analytic DSLs, you can use R or you can use, whatever. And there's database connectors, ADBC and ODBC. ADBC is for analytics, so that makes a lot of sense to use that. Anyway, we'd like to leverage this whole ecosystem for free. So we want to plug in object-based computational storage underneath this, push the analytic all the way down, at least the reduction part of the analytic, all the way down to the bottom, get an order or 2 orders of magnitude of reduction. Instead of a petabyte now, we're moving 10 terabytes. That ain't that much. You can move 10 terabytes, in a second. And we can. I mean, our networks are that wide. And we can deal with 10 terabytes trivially. Not, we have machines that are 4 petabytes, so that's not much of a machine. And we'd like for a data scientist to sit down in front of their favorite little data analytics tool and use it and go figure out how to do analytics on these big 100 petabyte size series runs. Trivially, we'd like for it to be simple like this. And we'd like for them to be able to use whatever their favorite tool is as long as it plugs into the Apache ecosystem. So that's the goal. Our use case is sort of going to be kind of like that. So our use case is the first thing we would do, we would write. Remember, we have these columns, this petabyte of columns, 100 columns. We're going to write out these Parquet files, and they're going to be row groups of some size, maybe 10 megabyte, 100 megabyte size chunks. So there'd be millions of them, and there'd be objects. So the LAN application would write fully formed Parquet things that are analyzable, write lots of them, and it would write it out to an object server. And the object server would then call into NVMe, a variant of SPDK that has something sort of an extension to the key value, but really it's object, so that you can do a put. And you can do a get. And you can do a delete and all those things, right? And so what we're trying to do is put together a demo of this functionality on the right side. And the first thing we did was we said, well, we're going to need an object server. And we looked out there and said, well, we'll use a MinIO gateway like everybody else. And we went, uh-oh, the MinIO gateway is being deprecated. Oh no, what do we do? Had a company called Versity. There's actually a talk about this tomorrow that I'm given part of, where we paid a little bit of money, and they're really smart people, and they produced a really high-performant Go-based object server. And it has a flexible plug-in mechanism at the bottom of it, so you can plug in whatever you want for put, and it's like Fuse, but for objects. And if anybody wants to use it, it's open source. We helped pay for it, and we're going to help them pay for it next year too. And actually, the person maybe in the room, maybe not, that did the work. And so anyway, we're trying to encourage, having some tools out there that work like this. And then we actually paid Air Metal, which is an analytics company, to produce a first generation variant of this stack where you've got a modified SPDK that has these puts and gets, and even a simple S3 select like function so that you can do a select and send the rows back in that way. And again, the data is at the bottom in Parquet. So anyway, that's getting the data written out. Querying the data, you've got this simple S3 select, which doesn't do much, but it does do simple reductions, single variable, not too complex. But what we're working on over on the right is this: how do we connect this up to this huge Apache ecosystem? And the way you do that is you use all these tools, ADBC, and use some query engine like Presto or Spark, and you use this S3, or you use this push down service. I don't know if you know how that works, but you take an SQL statement and you convert it into a graph. You've got the pieces that are reduction and the pieces that are sort and the pieces that are grouped by and all that kind of stuff. And anybody can volunteer to pull something off of that graph and say, hey, I can do this. And so this is how Spark essentially does push down analytics to storage servers today, is it pulls the SQL statement apart and says, oh, I know that person can go do that, and I know that person can go do that. So I'm going to farm out all this work using Kubernetes and all the cloud crap to get this done, really fast. So we're going to borrow all that. We're going to use all that technology to push down these queries, and as much as we can push down, as low as we can push it down. So if some of it would be pushed all the way down to the OCSA or OCSD, using this thing called Substrate. And then the answers to the query need to go back in this form called arrow. Arrow is this way to send, you don't have to convert everything to text and send it. It's a way to do query results in a stream so that these consumers can redo it. So the ADBC user will get the answer in the form that they want it in. And we have a bunch of partners in this. I'll talk about that on the next slide. So this is the plan. We already have some of this working. I guess should move on. So I was happy that Jason had a really complicated diagram with a bunch of arrows and stuff on it. And I wanted to have my own. So there it is. But essentially it's what I just said. So you can see that there's Presto or some user at the top using Presto. There's these file access methods and stuff. But anyway, to do a put, you use the S3 client, you write to an object server, the blue thing in the middle, and it puts it out on one of the SPDK targets as a put. Remember, it's a fully formed, analytic-friendly Parquet object. There'll be millions of those spread out across lots of these devices. And then the query, it would work like I said before. Presto would, you'd do an SQL statement. It would go down to the object server or down to this, push down service. We would use Substrate to pull the query apart. We would send all that down as low as possible, and potentially some of that reduction step can be run on the end object computational storage targets. We have some really nice partners in this. The main partner we have is SK hynix. They're a great partner in this. They're planning on doing a version of this OCS target, and they're also helping a lot with other pieces of it. We had this company called Neuroblade. Neuroblade is a company that makes a very, very high-end, essentially computational storage array device that does this analytic pushdown thing. They know a lot about analytic pushdown, so they're sort of dealing with the right side of this diagram. Versity wrote the web server or the S3 server for us. Air Metal did the original demo of this basic technology in using SPDK. But I think the most important piece of this is the only boxes that are proprietary are the ones that have the big red square around them. Everything else is open. In fact, we intend to publish this entire thing to encourage people to play around with it. And in fact, after Stephen talked, we were back in the back plotting how we should write one of these user space variants of this and just give it away. I might as well, so that people can play with this even in KMU. There's no reason not to. And anyway, this is the project that we're working on. We demoed already the initial piece of it. We want to demo more of it at supercomputing. So in November, more of it will be demoed. We probably won't have the analytics piece hooked up until spring. Probably we may demo that at International Supercomputing, although I don't know if I want to go to Germany, but anyway. So that's what we're going to do. Some of it's working already. These are the great partners we've had working throughout all of this. Wow, I forgot Seagate. Weird. They're small. There's nobody here from Seagate, right? Anyway, partnering has really been the key to this. This has really been how we've accomplished it. And then I tried to draw up a little stack diagram of what it might look like. You got your data agnostic computational storage over on the left, your KV server thingy in the middle, and this object concept over on the right. Anyway, I think that's about all I have to say. That's a Cray 1. That was serial number 5. And it's tall. It's about that tall. So at supercomputing last year, it was the 50th anniversary of Cray Research being formed as a company, 1972 to 2022. And they had the Cray serial number 1 in the booth at supercomputing, which actually was a Llano machine that we got in 1976. And everybody that had worked in this era that was at supercomputing walked by that and said, that's the shortest Cray 1 I've ever seen. What's wrong with this? And so anyway, the story is that they shipped this thing to Llano, and it worked great in Minnesota, and it didn't work at all at Llano. In fact, within a matter of minutes, it wouldn't even boot mostly, and if it did boot, it would die pretty quickly thereafter. It turns out that they hadn't protected the memory. Right, this was 1976. And so they had to protect the memory. And so they added a row of parity, another foot of that. So that's the way those banks work, is each one of the parity bits, or the bits, is stacked up in a module. So they added another row of them. And so they're all taller except for serial number 1. Serial number 1 is in the museum in Chippewa Falls. We have serial number 2 in our museum. We should really have both because we paid for both of them, but anyway. Somebody's probably here from HPE. It was really nice that they did that, put that up there. That was really a nice demo. Any questions? Just want to get to the bar? Yeah. Is it based on FPGAs? That's a good question. Some of it is and some of it isn't. The ABOF, where the offload was heavily pipelined and erasured, and so it was very bandwidth limited. That was done by Eideticom on FPGAs. However, that's really cool work because they didn't make it run on FPGAs. They would actually run on QAT if you had it. It would run on a processor if you had it, or it would run in an FPGA if you wanted to plug one in. So it was very flexible. The KV was run on regular ARM cores. The Kinetic is a baby, tiny 8-year-old ARM core. Anyway, so some of both. I think all this has more to do with memory bandwidth than it has to do with core. If you're going to put yourself in the data path, look at DPUs. DPUs today, most DPUs aren't in the data path. Most DPUs are in the control path, and they're used to give people bare metal access to hardware. You run the kernel in the DPU, and you just leave the processor. You can have the whole thing, right? And the reason that that's true is because building a processor that's a bump in the wire that runs at 200, 400, 800 gigabits a second is hard. You got to have a lot of memory bandwidth in your server to be able, in your processor to be able to do that. And so even today, most DPUs aren't terribly good at in the data path. That will change, but it's really memory bandwidth that solves these problems. It's not the processor. And when you buy a processor to put in a data path, that's the first thing you better look at is how much memory bandwidth do you have. Sounds like we can call it. Thank you for your time.